Hello friends, welcome to my video. So today we will be discussing NMTC 2023 Junior Problem 3. So today was the NMTC exam. So this is stage 2 level and I hope many people had a good exam. Let's start with this problem. So we are given that AI where I equals 1 to 6 are reals and this polynomial, this big polynomial can be factorized into linear factors x minus xi such where I is from 1 to 8. Okay. So let me first explain the question. It might because the notation might be a bit intimidating for some people. This basically means that a1, a2, a3, a4, a5, a6 all these are real numbers, right? And these are also real numbers as well. So basically all the coefficients are real numbers, and it's saying that it can be factorized into these factors x minus x1, x minus x2, so on and so on till x minus x8. So as you can see, it's written right here, right? So we need to basically find the all the possible values of a1, a2. We need to find the all possible values of a1, right? Find all the possible values of a1. That's also there in the question. Okay. So we will start with this question. If you use Vieta's relation, then from Vieta's relation you can see the sum of roots is 4 and the sum of roots taken 2 at a time is 7. Okay, and the main part is the x minus xi thing. The part here you need to understand is that this is a real polynomial, and by here they mean it that basically this polynomial can be written as the product of 8 linear terms, and the degree of this polynomial is also 8. So this means that it basically means that all the roots of this polynomial are real, and since all the roots are real, that gives a very good advantage to us. So let's discover what the question further is. So as you can see, we now want to find the value of x1 square plus x2 square plus so on till x8 square. This is the sum of squares, so that we can find some bounds and work on some stuff. So as you can see, x1 plus x2 plus so on till x8 the whole squared, which is nothing but 4 squared, so that's 16. And if we expand this out, you will get x1 squared plus x2 squared plus so on till x8 squared plus 2 times sum of roots taken 2 at a time. And as we know, this thing is 14, and then we have the sum of squares as it is. So if you just take this as 16 as 14 plus sum of squared, so you basically get sum of squared equals 2. So now we will be using two very important properties that we have found. Basically, actually three, because the first important property is that all x1, x2 till x8 are all real numbers, right? So let's see. x1 till x2 till x8 are all real numbers. Okay. We are also given that x1 plus x2 plus x8 equals 4 and x1 squared plus x2 squared plus so on till x8 squared equals 2. Now as you must have heard of the inequality called RMS-AM inequality, we can apply this inequality because all of these are real numbers, and that inequality actually works for negative numbers as well. So as you will see, the inequality states that that x1 squared plus x2 squared plus so on summation till x8 squared divided by 8 is actually greater than equals to the arithmetic mean, which is the sum divided by 8. So why the root mean square? Because you first take the squares, you take the mean, which is the average of the squares, and then you take the square root. So that is the root mean squared. So the root mean squared RMS is greater than equals to AM, which is the arithmetic mean. Okay. And why this applies when So we also need to justify why it is applicable when x1, x2 till x8 are negative. So it is applicable there as well, because this sum will attain its maximum value when all of them are positive, right? Any sum with like if these things have a particular magnitude, then the sum will be attained the highest value when all of them are positive. And if all of them are positive, then the inequality works. So it will obviously work when they are negative as well. Okay. And as you can see, we have x1 squared plus x2 squared. So basically this thing inside there, we have found that to be square root of 2 upon 8, right? And square root of 2 upon 8 is just square root of 1 upon 4, which is 1 by 2, right? And this is greater than equals to the average, and the average is 4 by 8, which is 1 upon 2. So as you can see, an equality is holding here, and since and there's a very important fact that that in this inequality, the equality holds only when x1 is equals to x2 is equal to x3 and so on is equals to x8. Basically all these numbers have to be equal. So all the roots of this polynomial have to be equal, and that basically means that if you have them as equal and their sum is 4, so like I can just write that the sum of them all will be just 8 times x1, right? So I'll just write here for that x1 equals x2 equals x8, right? So 8 times x1 equals 4, so x1 equals 2, and as you can x1 equals half, okay? And as you can see that half squared is 1 by 4, and when you add 1 by 4 8 times, you get 2. So this is satisfied as well. So this is one of the solutions that all the roots are half. And since and in the question we were asked to find the all possible values of a1, and as you know by Vieta's relation, a1 is just the product of the roots because it is the constant term. So x1 times x2 times x8, right? And if you just plug in the values, you will get half times half times half 8 times. So this is nothing but 1 by 2 whole to the power 8, and we know 2 power 8 is 256. So 1 by 2 power 8 is 1 by 256. And so that is the only possible value of a1. There is no other possible value of a1, and that is also the kind of beauty of the question, because there is equality case. So only one of the possibility is there. You don't have any other possibilities. So that this also makes the questions this question a bit easy. Although it looks tough, but it's very easy. It's a very easy question. So with that, I like to end the video. So this is the solution. If you like the solution, please like and share the video. If you like my videos, you can support me by subscribing to my channel. And if you want solutions to any other problems from NMTC, you can give that in the comment section, and we'll see you in the next video. Thank you so much.